Welcome everyone to the week 10 tutorial session of Algebraic Combinatorics MA19. I am Rati Ludhani, a PMRF Fellow at Department of Mathematics, IIT Bombay. Today we'll discuss sample questions related to lecture notes of week 10, which are related to Schur polynomial and writing it in terms of even the product like Schur polynomial into symmetric polynomials. So what does that give and all those theorem. So let's begin. Find k lambda delta if lambda is equal to 3 comma 2 and delta is equal to 1 1 1 like 5 times 1. So okay, I think I have kept the definition here maybe. Yeah, so okay, maybe, yeah, okay, so I can write it here. So what is this? Kostka number is what? K lambda delta. So this is Kostka number. Of shape 3 or maybe in general shape lambda and type delta. Okay, do you know how to find out this number? And firstly, what is shape and type of this number? What does this represent? Okay, just to recall, so if you need to find out Kotska number, so what does this say? You first, so the shape defines, so for example, let's consider this case. So lambda is equal to 3 comma 2. So this is the shape. So what does this say? This is like 3 blocks and this 2 blocks. So it's like Young's diagram for partition. So what does this say? You consider this three blocks in first row and 2 blocks in second row. So this just represent the blocks, the number of blocks in each rows. And if you have like 3 2 2, then you will just make two blocks here again. Okay, so yeah, so this is 3 and this is 2. So this defines the shape. So this will be the shape. Now what is type? Type says type delta. So for example, delta is given to be 1 1 1 1 1. So this says you consider 1 ones. So whatever this is, the position will say you consider that many ones. So for example, ones, twos, 3. So this is for example 1 ones, 1 twos, 1 threes, 1 4. I'm just writing apostrophe, just like these many numbers. So for example, if delta is equal to, let's say 3 comma 3, maybe, or like maybe we can take 2 2 1. So this will be 2 ones, 2 twos and 1 threes. So this actually represents how many ones you will consider, twos you will consider and threes you will consider. So you have 2 ones, so you have this, and you have 2 twos and you have 1 3. So these many numbers you have. Now you have to settle these numbers in this block so that the in the row it should be weakly increasing, and over the column it should be strictly increasing. So we need to consider that. So is that clear how we are writing delta? So what delta represent, what type is used for? So in my question is this. So we can consider this also if we want later, but let's stick to the question right now. So you have delta is equal to 1 1 1 1 1. So you need to consider 1 1. So you have 1, you have 2, 3, 4 and 5. So you need to consider 1 1 1 2, 1 3, 1 4, and 1 5. So these many numbers you have in your hand. Is that clear?
Ma'am.
Okay. So clear, right? Okay. So now you need to put this numbers in these blocks. Okay. So these 5 blocks you need to put these numbers. Now such that in the row it should be weakly increasing, and over the column it should be strictly increasing. So how can you do this? So let's see. So you have this. Now what can you do? You put 1 here, and then maybe 2 here, and you don't have again 1. So you can put 2, but over the column, sorry, over the row you can have strictly weakly increasing thing. So weakly increasing means you can have 1 1 2, you can have 1 2 3, which is strictly increasing, but you can have weekly thing. So you can have 1 2 2 also. But okay, but we don't have we have 1 to 5 only 1 1 numbers. So you have 1 2, you can keep it here 3. And now what you can do at this place, so for example, at this place you can keep 5, and here 4 and 5. This is definitely an option. Okay, because this follows like over the rows, uh, weekly increasing, it should be weekly increasing, and over the columns it is strictly increasing. Okay, so as you can see, this is 1, this is 4, so this is increasing. So for example, what could not be an option? We need to figure out how many are there, but let's see what could not be an option. For example, you keep here 2 1, and let's say you keep here 5 and 3, 4 and 5. Then if you this should be increasing, so that should be 1 2, let's say. Now what can you keep here? Because if you put 3 here, which is the only option for you, 3 you can keep now. But this is not increasing, strictly increasing. Are you getting the point? How we need to figure out? So this cannot be okay, this cannot be a option for this. uh, okay, right. So let's see how many are there. Okay, so okay, you have 1 2 3. One option is definitely this. Let's see what other options you can have. So you have to keep, like for example, this is not an option. So you have to start with 1. There is no other possibility for this position. So you have to start with 1. Now let's see at this place.
4,
Yeah, 2 where? So for example, if I number
1, 3, 4.
1 and here,
First row 1, 3, 4 and 2, 5 is correct, ma'am.
yes, 2 5 is correct. Very good. So yeah, you can always start with all the options. Right, very good. So you 1 is fine. Now 2 could be here. This you have taken. Now for example, if 2 is here, then you can keep 4 here, and here 3, and let's say 5. That is always an option. That is also an option. So okay, looks like there are too many options. So 1 is fixed. Now these 4 positions need to be decided according to what we need. So for one thing, it should be in order. So this, let's see. So 1 we have taken. Now we have taken the option of let's fix some place and see all the options. Like when you have taken 2, so I've considered this to be 1, this to be 2. I'm just keeping it in a pattern. So 1 2, I am fixing 2 here at this position. Okay, so now if this is 2, what other possibility you can have? If you keep 5 here, so you have kept 3 4 and now 5. If you put 5 here, then what can you have? You can have 3 4. That is also okay, right? So this is third, but you will not have anything else, because this position, if you fix this position, the other two will be definite, because that should be in increasing order. You cannot swap in the second row. Okay, so these three options are there with 1 2. Okay, now let's see if we switch things. So whenever you need to figure out these things, keep it in a pattern so that you will not forget to consider something. Okay, um, one option maybe. So let's say 1 is there, 2 is now gone. Now let's take 3 here. If you put 3 here, then the only option for 2 will be this, right? Now here 3 is there. Now you can have 4 and 5 both places. Okay, so you have two options here with, so for example I'll write with uh, three options with this. Okay, now you have two options with this condition. You have 1 and 3. Okay, now let's see, because if 1 and 3 are there, then 2 has to be here. Now let's see the next one. So now if you have, for example, you're considering all the options. Now you keep replace 3 by 4. Then can you have that? Can you have something like can you get some tableau with this 1 4 something? No, right?
No, ma'am.
Yeah, because 2 3 and you cannot have this. So no. Okay, no option. Okay, similarly for 5 also, or 5. Okay, now let's see the next one. Now you have exhausted all the options of this place. Now let's see if you switch this place. Okay, so if you consider 2 here, one second, one second, I think all is done. Yeah, yeah, certainly, because you considered this place and you considered all the options. So if you switch this place, then there will be something with anything, like, I mean, so what I mean, okay, this is bad. So you have 3 and you have this and this. Okay, so when you considered all the options with this position, then you have considered all, because if you keep here something, then this will give some number to this position, right? The position which the for which we considered all the cases. So that will be considered. So for example, this one is already considered here. So these are all. Is that clear why these are all? Okay, so you have so k lambda delta should be what? K lambda delta, this is the number of, okay, number of all the options you can have. So you have 2 options, 3 options, and there is no option. So you have total 5. This number is 5 for the given lambda and delta. Okay? Yeah.
Ma'am.
Okay, so this is how we calculate that. Calculate k lambda delta. And note that if you switch delta and lambda, for example, if you say it k delta lambda, then it will be something else. So it will be the shape and type will be switched. So according to that, you will have some other number. Okay, and there is a relation which is given in the next lecture note, which is from week 11, but I'll use that in the today's tutorial. So yeah, let's keep it moving. We'll come to that. So k delta k lambda delta you need to find out. Now lambda is given to be n minus 2 1 comma 1. So this is your shape, and now delta is n minus 3 2 comma 1. This is your type. Now shape says you considered accordingly the blocks. So n minus 2 in the first row. So first row is like n minus 2 blocks. So okay, n could be anything, so it's just general thing. Now 1 and 1, so you have 1 in the second row and 1 in this third row. So this says lambda is this is lambda. Okay, now let's see what do we have now. This is the shape. Now you need to find out the type of type with this. So lambda is n minus 3 2 comma 1. So what does this say? You consider n minus 3 ones, 2 twos, and 3 1. Sorry. So this number says 1 3s. So you consider 1 3. Okay. So let's see. So n minus 3 ones. So if you consider, so you have to start with 1. There is no other option, because in the second row it should be less, and on the right hand side, so if so one cannot, if there is 1, then it cannot be at some other place. So the main thing is, for example, if lambda is 0 to 1, then there is no 1. So in that case, one could be so in that case, this first block should be something, could be anything. But at this place, when 1 is there, because if you put 2 here, for example, then you cannot have 1 in this row, or even in the columns. You cannot have anywhere 1 could come, because of the restriction of this strictly increasing and weakly increasing thing. So you have to start with 1 if 1 is there. Okay, so let's see. So you start with 1. Now you know that over the column it should be strictly increasing, so you cannot have, it should be strictly increasing. And let's see, you have 2 2s and 3 1 3s. So that means what can you have at this place and this place?
2 3 1 only, ma'am.
Yeah, 2 3 only, right? Exactly, very good. So because you know that this should be strictly increasing, and you have the number still 3 only. You don't have 4 and 5. You don't have that. So the only options are 2 and 3. And if you have, for example, 4, then you can have 1 2 4, or 1 2 3, or 1 3 4. You can have that, but right now you just have 2s and 3s. So that means the first column should be 1 2 3. Now let's see what do we have at these places. N minus 3 ones. So n minus 3 ones, it should be strictly increasing, right? So this should be what? 1 1, because it is increasing. So these are n minus 2 blocks, so you will just be remained with 1 block. One more thing, what do you have extra? 1 2s. So you have 1 2, and there are n minus 3 ones. Okay, so because other you have already exhausted, So you have 1 1 1. For example, you can now you have 1 and 2. Again, you can only have weekly increasing things, so you cannot have 1 2 1. So the only option you can have is 1 1 1. You go on and stop at here because you just have n minus 3 ones, and you put 2 at the end. This is what we will get. But do we have any other option with this condition, with this shape and type?
No, ma'am.
No, no. Okay, great. So k lambda delta with this conditions, with these values, is just k lambda delta is 1, because you have just one possibility for these blocks. Okay, great. And for example, okay, even for example, you have if I just say lambda is equal to n minus 2 1 and 1, and delta is n minus 4 2 comma 2. Now how many will you have? Now what I did, I did certainly you consider n is bigger than 4, or even strictly maybe 0 is also fine, but that's okay. Let's say uh, n is 5, uh, yeah, n is greater than or equal to 5, let's say. Then n minus 4 2 comma 2, you consider that you have n minus 4 ones and 2 twos and 2 threes. Now what is happening? You have 1 3 extra. Then how many options you can have? So you consider this. Now again you have 1 2 3 possibility, because there is no 4 here. You don't have the number 4. So you have this. Now you go up to n minus 4. Now you have 2 blocks which are in the end. So because this is n minus 2, because lambda is this. Now out of these, n minus 4 is already 1. Now you need to see what are other two. The last two will be what? Last two, you have the option 2 and 3 only. So okay, yeah, so you will have here 2 and here 3. Again you have just one block. Is there any other option? No, right? Because again you have to keep it weekly increasing. Basically you cannot have decreasing. So this will be just 2 and 3. Is that clear how we are
Yes, ma'am.
calculating the number? Okay, great. So let's move to the next question then. Consider the partition mu 3 3 1. Yeah, so the number for this also, k lambda delta, is just 1. This is important to figure out, because this will actually give a sure polynomial whenever you need to calculate. So it's good to learn this. So 3 2 1 1. If mu and lambda is this, consider the partition mu 3 3 1 and lambda equals to 3 2 1 comma 1. Then find the value of k mu lambda. Okay. So now,
Ma'am, what is the difference between K lambda delta, K lambda mu?
oh, k lambda delta is lambda mu or k mu lambda? You mean this?
Lambda delta. Before previous question, we
Yeah, okay. Lambda delta. It's just lambda. You can have lambda delta, mu lambda. You can
the
have any.
delta means we write 0 n minus 2 time n minus 1 time 0 up to etc 0 time, and matrix formation A lambda plus delta.
Yeah. So what is the difference? It doesn't matter what number you use, like what letter you use, what Greek letter you use, but the point is the first letter will denote shape and the second letter will denote type. That is the main thing.
Okay, ma'am.
Shape says you consider that many blocks, the shape of like this shape, this n minus 2 1 1. So this shape, so first letter will denote the shape and the type will give you the ones, twos and everything. This is the important thing. Whatever letter it is given on the first place, that will denote shape, and the second letter will denote type.
Okay, ma'am.
It doesn't matter which letter you use, that is not important, but whatever it is, that will denote shape and type. So the normal is the shape and type. So it should be in this order. If you change the if you switch delta lambda, you have to consider first one to be the shape and the second one to be the type. Letter doesn't matter.
Okay, ma'am. Thank you.
Yeah, sure. So find the value of k mu lambda. So this and this represent different things. Okay, this represent that lambda is your shape and mu is your type, and here it will represent mu is your type, sorry, mu is your shape and lambda is your type. So these are that. So right now whatever we have, like first letter, you just think of the shape. So you have mu to be equal to 331, which will be your shape, and lambda is 3211, this is your type. Okay, now let's calculate that. Again, what we will consider. Yeah. So what we will consider is shape. You have 331. So first row will have I'm just 331, so I'm doing this. Okay, so this is mu. So mu is 331. So first row will have 3 blocks, and second row will have 3 blocks, and third row will have 1 block. Now we need to calculate this k mu lambda. So let's see. Again, what does type say? Type says you consider 3 ones.
3 ones,
Yeah.
2 2s, 1 3s, 4 1s.
Yeah, exactly. Very good. So now let's see how can we fit that in this with the constraints that the row wise it should be weakly increasing and the column wise it should be strictly increasing. So that we need to consider. Let's see. So this comes from the theory. If you go through the lecture notes, it is coming because of this horizontal row thing. The horizontal, if it is on the horizontal boundary, then those things will be used to say that we are why we are considering weekly increasing and strictly increasing for columns. Okay, so let's see. We have 3 ones. Again, you have to start with 1. If 1 exists, then it should be on the first block, definitely. So this is 1. Now, so again, where can you start? So if I just say these are A11, the block name, so can you tell me? A13, in the matrix form, I'm just writing what is this. Okay, this is A31, and for this is A22, and this is A23. So can you tell me where should I start or anything?
First row fully 1 1.
Yeah, exactly. Because there is no other option, right?
Yes, ma'am.
Because over the column you have to go strictly increasing.
2 2 3 4 or 2
Two,
2
two.
4 3.
3
3
4.
4
Exactly. Very good.
or 4 3.
or 4 3.
2 to 4, 3.
Right, because the only options, so how can yeah, 3 and 4 will be switched. Oh, sorry. So 3 and 4 will be switched, right? So what we are saying, just to not miss anything, these are exactly what we need. Very good. So 1 1 1 will be there, and here what can you have? Either you can have 2 3, or you can have 2 4, or just say you can have 3 4. But whenever 3 will come, then 2 cannot be there, so you cannot have this option. Okay, so or you can have 2 4. So let's see, if you have 2 and 3, now 2 have to be here because there is no other option, because this is weakly increasing and you don't have anything uh, any place where 2 can be like kept. So this is 2 2. Now you can have either 4, and if you consider 2 4, then you can have 3. Exactly, these are the only two possibilities we can have.
Ma'am, row wise repeated is not necessary, ma'am.
Which one?
Column wise, column wise. If row wise 2 2 means in column wise we can't write 2 2.
Column wise we will not write 2 2. Sorry.
Now we are writing 2 2 row wise.
Yeah.
The same way we can write 1 2 2. It is possible or not? I'm asking
Oh,
question.
okay, so you are saying in the row or column? 1 2 2, where exactly you are putting?
One first row 1 1 1
Yeah.
2 3 4 2.
No, no, this is not possible because over the columns should be strictly increasing. Strictly means you cannot have equality.
Okay.
Yeah, this should be so whatever, if you say mu1 mu2 mu3, I don't know, this should be strictly increasing. There is no equality, but over the rows you can have equality. So a1 a2 a3, let's say this is be strictly increasing if, just as the definition, if a1 a2 a3 is like this and weakly increasing if a1 less than or equal to a2 less than or equal to a3. So it could be equal, but for strictly increasing it has to be like equality cannot be possible. So that is the difference. And over the columns we are asking this should be strictly increasing, we are imposing the condition. And over rows we are considering the weekly increasing condition. Okay, is that okay?
Yes, ma'am.
Okay, great. So in this question, what do you have now? K mu lambda will be what? You have two options, 3 and 4 can be switched. So K lambda delta, or I don't know what I considered, K mu lambda. Doesn't matter which letter will be there, but just ensure that whatever you are considering, it should be with the, like, this should be the shape, this should be the type. Just that. Okay, great. Let's move to the next question then. Okay. Okay, I kept it here just for maybe what I can do. Okay, anyway. So what we are saying here, okay, let me just, okay, so the question says, right, so for example, question says, if lambda is equal to 2 to 1, then this is the partition, then find s lambda x1 x2 x3. You need to find out in terms of mu, that means in the monomial symmetric polynomials, you have to find out sure polynomial in terms of that, right? So what is the sure polynomial? If you recall, this should be what? Alternate a lambda plus delta x1 x2 x3. Yeah. And
I yield.
yeah, and what is delta? Delta is this, right?
Yes, and up to etc. 0.
Yeah, and with n is equal to 3, with n is equal to 3, what will we have? If n is 3, because 3 is there, so this will be just 2, 1 and 0. So the question is asking basically what is 2, 2, 1, x1, x2, x3, and this is a lambda plus delta, that means you add 2, 1 and 0, so you'll get 4, 3 and 1. This is actually making it strictly increasing, and this is 2, 1, 0, x1, x2, x3. As you know, this divides the numerator, that's why it's okay to say this is a polynomial, because this will divide it. Okay, now this is, in general, is very hard to calculate it using this notational formula like this way, because you have to alternate is a determinant. Now you can consider the so so you can I guess, you can consider the Beckers and try to, you can try to do that, but yeah, it is very hard to calculate. Okay, but there are ways. So there are theorems basically. The one thing is, okay, I'll go to lecture notes what I wanted to say. This is Pierre rule. Yeah, so what am I saying? So these are the notes related to the next week, which is week 11, which actually gives the first lecture of week 11 is related to writing sure polynomial in monomial symmetric polynomials. So I'll use that formula and do that. So yeah, so this is one, and better I'll use a theorem. So this theorem says, okay, this is a corollary, and maybe, yeah, exactly. So this theorem means this value, okay, x lambda mu is equal to k lambda mu, which means this value s lambda x is equal to summation this is k lambda mu is m mu x. So what I want to say, if I use that theorem, I can say this thing. So by a theorem in the lecture notes, monomial expression of sure polynomial from week 11, we have s lambda x1 x2 x3 is equal to the summation k lambda mu m mu. Okay, so this will be the sure polynomial, and we'll use this polynomial to calculate that. That's why I was saying, it's if you know how to calculate Koska polynomial number, then you can easily calculate what is the sure polynomial. Okay, let's try that. Okay, now I can add that. Yeah. Okay, so I'll use this formula as lambda x1 x2 x3, and this is summation mu partition of, now cardinality of lambda. Now what is lambda in our case? This is 2 to 1. So what I'll do, I'll write here also as 2 to 1, and here you will get 2 to 1, the sum will be what? 5. So 5 comma 3, because there are 3 x size, n is equal to 3, summation, and k lambda mu, and this is mu. Okay, so this is as I said, the first letter will represent shape and the second one will represent type. Okay, so let's try to do that. Now lambda we know. Okay, if you want to write it here also, so you can do that. 2 to 1 mu. So if you are confused, you can use comma also, because this is not a permutation thing. This is mu. Okay, so let's try to do that. Right. Okay, so what do we need? We'll consider all the partitions with 3 blocks. So p5 comma 3, what does this represent? You partition 5 in 3 blocks, you cannot go beyond that. So for example, so p5 comma 3 is what? You consider 5. So for example, you can consider the partition 5. You can next consider okay.
Degree is 5 and the number is 3.
Sorry,
N equal to 3 degrees.
not degree. Right now I am just considered what are the partitions of 5 with 3 blocks. 3 blocks means, so for example, you can have the partition 5, you can have 4 plus 1, you can do this partition. Next so basically, if you want to represent in this form, this is the form. This is 3 plus 2, 3 plus 1 plus 1, this is 3 1 1. You can keep zeros later on if you want. So for example, 5 0 0, if you want to write it in this form. So 3 1 1. Now 2 plus 2 plus 1, so this is 2 2 1. Now you cannot go with this. So this is not an option, because you need only 3 blocks. 3 blocks means 3 positions only. So you cannot have that. Even 1 plus 1 plus 1 plus 1 plus 1, you cannot have this either. Is that clear? What is partition of 5 comma 3? Like,
Yes, ma'am.
okay, you partition 5 with 3 blocks. So we need to find out the Koska polynomial for all these 5 options. So let's try to calculate. Okay, yes, right. Okay, so let's begin with so you need to find out. So first you have 2 to 1 and mu is 5. Okay, so shape is shape is 2 2, and this is 1. So you have this. So because first one will represent shape. So shape is fixed because lambda is fixed. Now you have the fixed shape. You have ones and twos, which could be anything. So right now this represent the type. So this says you have 5 ones. You have 5 ones. So you can have now you have 5 ones. That means the only option is you have 1 1 1 1 1. Okay, can you keep it here? For example, you can start with 1 and you can keep 1 here. Can you have 1 here at the next position? This position?
No, ma'am.
No. exactly. Yeah, very good. So this is this one you cannot have, so you cannot go beyond that. So this is not a, so this value k2 to 1 comma 5 will be 0. Now let's see what about k4 comma, sorry, the first one is your shape. So this is 5, sorry, 4 1. So this what will be this? This is type and this is shape. So again what we will do, we'll consider this. Okay. Now let's see. Yeah, shape is 2 to 1 and type is 4 1. So you have 4 ones and 1 twos. Yeah. Okay.
Not possible one.
Not possible. Again the same thing. You can have 1 1, but not here. You have to
Here
have
2
some.
means here 1 will come.
Yeah, exactly. So sorry. Yeah. So this is again not possible. K2 to 1 4 1 is equal to 0. Let's see the next one. This is 3 comma 2. Now you have 3 ones. Sorry. 3 ones.
Possible, ma'am.
Hmm? Sorry.
Not possible.
Again.
If second row is 2, 2 means third one only one
Exactly.
remaining, and the first row we are sending one.
Mm. Yeah, exactly. Yeah, very good. So this is again 0. Yeah, your voice is breaking. Okay, let's see the next one. 1 second. Next one is K221 and 311. So let's see this. K K
Not possible, ma'am.
again,
Not possible.
not possible. Uh, yeah, right. This is again not possible because you can have one. Right, you can have 1 2 3 here because you have 3 ones, 2 sorry, 1 twos and 1 threes. So you can have 1 2 3, but you have one option. Right, you cannot. And one more thing, if
Yes,
you
ma'am.
see in the rows, there are 3 rows. So the first column has to be 1 2 3. So at least you have 3 firstly. So in the other option, in the here on till this place, you don't have 3 itself. So you can directly discard that possibility. Now this one also has this problem because the problem is at least if 3 is there, then this option has to be something like bigger number. That is again not possible. Okay, let's see the next one then. 311 is done. Now you have
2,
221.
2, 1.
Yeah. Do we have any?
Here we can write, ma'am.
Yeah. So how exactly?
First column is 1, 2, 3, 1, 2.
Yeah, exactly.
First column 1, 2, 3.
And
Second column 1, 2.
1 2, exactly. Very good. So when this is equal, then we will have definitely one option, like exactly one option. This you can check in general. So this will be 1 always. Like if you have lambda lambda, this will be always 1, because the only option you have as per this. And you will have first row will be 1, second row will be 2, third row will be 3, fourth row will be 4. Whatever it is, it will be exactly this. There will be no other option. Okay, very good. So k lambda lambda is equal to 1. Okay, now let's see the next one. Do we have next one? No, because we have till 2 to 1 on. Sorry, we have till 2 to 1 only. So so sure polynomial will be what? Summation. So summation, now it is over mu, and this you have k lambda mu, and you have m mu. So you'll have something, yeah. So you have just non-zero value with k lambda lambda, which is 221 221. So this will be what? M221, and you have this equal to 1, and everything else is 0, like you have just 1 this. So M221, you can even write it down as exercise. So what will it be? X1 raised to power 2, x2 raised to power 2, x3 plus x2 square x1. You do permutations, and next you can have yeah, x1 square x2, sorry, x3 square and x2. So this is exactly M221. So this is the monomial symmetric polynomial. So this is the sure polynomial of our question. Or maybe I can write where lambda is equal to 2 to 1. Is that clear? How are we calculating sure polynomial?
Yes, ma'am.
Okay, great. So this is in terms of monomial, or you can, but yeah, the question was to write it in this form. You can always write it in the other form also, exercise form. Okay. One second. Yeah. Okay. I think I have the solution also here. Let's try with okay. Yeah. Oh, I kept the same one, 2 to 1.
Eighth question.
Yeah, same. Oh wait, this was right. No, this question I meant. Okay, this question is not this I explained earlier. Yeah, this is the same thing. I copied that question earlier. That's why it is the same. The question which we did. Never mind. Let's move to this question. So, what do we say? I forgot. Young top tableau. Yeah, semi-standard tableau. So, okay. So this is the form, in the sense like you need to find out the symmetric sure polynomial with lambda equals to 2 1 1 with x1 x2 x3 in these terms, and you have s lambda x1 x2. So what I was saying, this is the form in terms of x. Again the same thing, if you do it for m, so actually these are the same things, that is nothing new, but I'll try to explain how exactly. So what is k? Okay, what is k lambda? I'll change the color. What is k lambda mu? This is the cardinality of how many SSYT, like semi-standard tableau, you can have with shape. Shape is fine. Shape lambda and type, or maybe not type. One second. Okay, take care. Actually, I'll explain why I was not writing earlier. Okay, I think so. This is the cardinality, but now you need to find out how many semi-standard tableau you can have, and so if you club them, if you add them, you will get the monomial symmetric polynomial, and you get the coefficient to be k lambda mu. So this is the expanded version. Even if you get this, you can have the other one, or you can say other way around. That is both fine. So let's try to calculate with a semi-standard tableau. What does that mean? I'll let you know. 1 second, I need to connect the charger, otherwise it will get switched off. Wait a minute. Okay. So yes, where were we? Find S211, x1, x2, x3 in terms of xi's. Okay. So yeah, this is a formula which we need, but let's try to do without using Koska polynomial. Sorry, Koska number. So what does this say? What is semi-standard tableau? You have so right now shape is lambda. So how will you calculate? So you consider the shape. Shape is given to be 2 1 1. So what will you have? You have two blocks in the first. Sorry. In the first row you have one block. In the second block you have one. In the third block you have one. So this is 2 2 1. Now, yeah. Now you need to the you have to fill, you have to do the filling of 1 2 3 4 up to and so on n. Right now n is equal to 3. So you have 1 2 3, you have three numbers. Now you can repeat it as many times you want. Okay, now we are not fixing mu, we are just saying you consider. So basically this is the same thing what you are doing. You will consider just 1 2 3. Okay, 1 second, it's not showing. Let me present again. So yeah, this is the thing. You have yeah, n is equal to 3 and this is 1 2 3. Okay, so now what we are saying, so you have the numbers now. You don't have how many times you should consider. So you need to figure out the numbers you can keep in this in these blocks, so that the row wise it will again be weekly increasing, and over columns it should be strictly increasing. The again the same conditions you will consider. Okay, but now you can consider as many times you want, ones, twos and threes. So wherever you will get something, some option, then you will keep it as the type. Okay, so I'll tell you what is the relation between these amps and x uh, okay, so let's see. So now you have actually, sorry, wherever you will get what you wherever you will uh, so you will consider these one two threes as many times you want. Wherever uh, you will get these blocks to be as you want, then you will consider back, you will consider the corresponding mu in your case. So this is the relation. So let's try to do that. You have 1 2 3, the three numbers are there. So first column has to be 1 2 3 because it should be increasing, right? Is that clear?
Yes, ma'am.
Okay, so now what can you have in this fourth block? You have
We
the
can
hmm, right.
1 2 3, anything we can give.
Yeah, exactly. You can give either one, either two, either three. So, with all these three, that's okay. We'll get whatever we need. So, you have one, two, three. Now, let's try. So, you can keep anything. So, you have three options. So, 3t such that you will get something here. So, let's try to do that. S lambda x1, x2, x3. This is the sum over t with this SSYT and this one x type t. Now what type t says? T is exactly, now type is what you consider. Now in the first case you are considering, in the first case you have two ones, uh, one twos,
2 1 1
exactly. So you will have two one
1
one.
is
Yeah, so you will in the type you will get x1 raised to power 2, x2 raised to power 1, x3 raised to power 1. These are the powers exponents for x size. Plus next one, this corresponds to 2 1 1. Now the next one you consider here 2. So you have the other one, you if you consider here 2, then what you will get, 1 ones, 2 twos.
1 1 x2 2 x1 3s
Yeah, so this will be
x1 1 x2 square
yeah,
x3 1
exactly. So you will have x1, x2 square, x3, 1 1, and
plus x1 x2 x3 square
yeah,
1 1 2.
exactly, x3
Next option.
yeah, yes, exactly. Very good. We'll have 1 1 2. So can you see here what is happening? So this is exactly what M211, right? This is M211, the monomial which corresponds to this, because it will have all the monomial symmetric polynomials, right? So sorry, the monomial symmetric polynomial is whatever you consider this, you'll consider all the permutations and you'll get whatever you need. So this is exactly M211. So when we consider mu, we always write it in the decreasing order, like 2 1 1. You have always this decreasing order. Mu is always with decreasing order. So when you will try to calculate with this Koska polynomial, sorry, Koska number, then what you will do, you will just consider mu to be 211, and uh, if you consider any other thing, you will not have anything, because this 1 2 3 is required. So you will get non-zero number when you will have mu to be 211. So this is exactly, so if you try to calculate with just Koska poly number, and as in this question, right, this one, as in this question, you'll get in terms of monomial, and this is the same thing as if you want to write it in terms of excise. So is that clear how we are these mm, so this is a theorem and corollary in the lecture notes, so these are related directly. So is that clear how we are calculating the Schur polynomial? So this is the Schur polynomial corresponding to 2 1 1. Is that clear?
Yes, ma'am.
Okay, great. Let's move to the next part. So you can calculate it wherever you need. These are kind of simple because we are getting for just one, uh, like Koska number to be Koska number, sorry, Koska number to be non-zero for just one option, for just one partition, but not for others. So you can try the bigger ones. So these are there in the exercises also. Okay, I hope you got the idea. Okay, let's try uh, to how to use labeled abacus to find out what is a plus lambda and everything. So I just wrote these definitions from the exercises only, this assignment thing. So this is not a question actually, this is just a theory, or maybe recall. So a labeled abacus with n bits is a word a0 a1. So you have this. I'll explain. So a0 a1 up to and so on, such that the subword of non-zero letters in a is a permutation of 1 to n. So how we are doing? Yeah, let's consider this example only. Okay. So the example, so you consider A to be 3200406510 up to and so on. Okay, you have this. So this AIs, this is the notation A0, A1 up to and so on, such that the subword of non-zero letters, you consider the non-zero letters in this, uh, is a permutation of 1 to n. It is a permutation of 1 to n. That means because n is usually your number of variables, so you are considering the permutations of those numbers, and the sign of a is the sign of that permutation. So the sub okay, and the support of a is the set support a. Ak is non-zero, so support of a is what you consider the position. So k is what, these are the positions 0 1 2 3 up to and so on. So the position is your k, such that ak is non-zero. So place uh, non-zero place, you consider that set, you will get support of a, and the weight of a you consider the in terms of x, powers of x. Okay, I'll explain here. And the shape of an abacus a denoted by sha, so shape we considered earlier, is the unique partition lambda with at most n parts, such that support of a is the set of parts of partition lambda plus delta n. So you consider this where delta n is this. So you need to remove this delta n, which we usually do with the Schur polynomial. So you remove that because this makes it strictly increasing, so you remove that. So now, yeah, for example, so you consider this example a to be this, and now how we are doing that. So you consider a this. Okay, now I'll draw everything. So this is your labeled Bekai. So you have, what you will do, you will first write all the numbers. So these are the, this is a0, a1, a2, a3, a4, a5, a6, a7, a8, a9, up to and so on. So what you just do, you can write it till so you write the positions. So this is 0, sorry, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can go on, but that doesn't matter because anyway we this is still 0. So here non-zero are so here n is equal to, so 1, 2, 3, 4, 5, 6. So n is equal to 6. So this is the permutation of excise. Okay, so 1 to 6, this is the permutation of 1 to 6, because you can see non-zeros are just 6. Okay, now you wrote the position. Now what you do, this represents the xi, where so this, so if you see there, so this is your k, this is the position 1 0 1 2 3 4 up to and so on, and the numbers are xi, sorry, xk. So what I am saying, so firstly see wherever you have non-zero thing. So at 0 you have something non-zero, at 1 you have non-zero, at 4, a4 is non-zero, next a6 is non-zero, a7 is non-zero, and a8 is non-zero, right? Now I'll put here what are the x's here, xk's are here. So this is 3, so that means this represents x3, this represents x2, this represents x4, this represents x. I'm just writing this number to be, because that says xak, because if you see there, weight is what, xak power k. So ak is the number which is written at that position. So x6, x5, and this is x1. Okay, you have this. Now what do we need? Right, yeah. Now what do we need? You have 0 1 2 3 up to and so on. This is x3, x2, x4, these are all. Now what will be your, so let's start with sign. So firstly, what is sign? Sign of a says where so this represents where xi's go. So that I can show you here, that will be easy. Just to not confuse you. Okay, where it started. So I'm just checking. It must start with right. So I'm just checking, is it the case? Yeah. Sign of the permutation obtained by reading labels from right to left. So you start with right. So this is like, you can see this is sigma 1, sigma 2, sigma 3, right? So what you will do, so what does this say, where 1 is going? So 1 is going to itself, as you can see. This is sigma 1, this is sigma 1, this is sigma 2, this is sigma 3, the letter, this k, sorry, ak. This is sigma 3, sorry, 2, and this is 3, this is 4, this is 5, sigma 5, and this is sigma 6. Okay, so what does this say? 1 goes to 1, 2 goes to 5, 3 goes to 6, and 4 goes to 4 uh, uh, in sigma, and 5 goes to 2, and 6 goes to 3. Okay, so let's see. So this is a bijection. Obviously, you just need to find the permutation which it represent. So 2 goes to 5 and 5 goes to 2. So this is a cycle. 1 goes to itself, no need to write. Now 3 goes to 6 and 6 goes to 3. So this is 3 goes to 6. So you have this cycle. So what will be the what will be the sign? Sign is just you can count here also like disjoint cycle. So this will be just 2, right? Sign of A will be 2. Sorry, power 2. So minus 1 raised to power 2. So this is 1. So sign of A is 1. Okay, again, we'll share again. Stop sharing. Yeah. Okay, is that clear? So sine is 1. Now let's see other things. So sine we can get now. So just consider, yeah, is that clear?
Ma'am.
Okay. So let's see the next thing. You need to find out the support. So support of A is all those K such that AK is non-zero. So support says support of A is the set of all those K such that AK is non-zero. So the positions. So that means AK is non-zero means these positions you are asking. So this is 0, 1, 4, 6 and 8. So this is 0, 1, 4, 6 and 8. So K represent the position like place. Yeah, position. So support is fine. Next let's see weight. Weight of A says, so these are K's and these are the X AK.
Ma'am, 9 also comes now. 0, 1, 4, 6, 8.
Yeah, 9 is also there. Right. Yeah, I forgot that. Thank you. So 9 will also be there because x1 is there. So yeah, weight of A is the product x AK power k. Right, over k you'll just take. So what it will be? You consider the non-zero. So non-zero one will only come in your thing. So here you can see you have at x0. So at subscript you will write ak is your 3 and power is your position. So x3 raised to power 0, x2 raised to power 1, x4 raised to power 4, x6 raised to power 6, x7 raised to sorry
X5 raised to
yeah
8.
7 and x1 raised to power 8.
X1 raised to 9.
Right, exactly.
9.
Ah, yeah, why? Okay, I
X5 raised to
forgot.
8. 1, 2, 3, 4, 5,
Oh, okay. Oh, sorry.
5, 6, 7, 8, 9.
So this is this, this
X4
is
raised to 4.
yeah
5,
6,
6,
7,
X2
8.
raised to
Yeah,
6.
actually this is 8. This is not 9. That's why. So this is 9. This
Okay,
position.
ma'am. Okay,
Yeah, I
ma'am.
was. Yeah, that's why. Yeah,
Uh,
this will not be here.
0, 1,
Yeah, so this will be this.
4, 6, and 8.
Yeah, 7 will also come.
7, ma'am.
Yeah, 7 will come. Here it is already there, right?
Yes, ma'am.
Okay. Yeah, so this is how we get weight and support. And what left? Uh, Shape of A. Shape of A is the unique partition lambda with at most n parts. So you need to find lambda such that the support of A is the set of parts of the partition uh, lambda plus delta n. Right. Okay. Not written. Okay, that was not in the question maybe. Yeah, so is the set of parts of the partition lambda plus delta n, and delta n is n minus 1. So n is your 6. So delta n is what? N is your 6. So this is 5, 4, 3, 2, 1. So you need to consider lambda. Lambda is what? Lambda is the unique partition lambda with at most n parts. Yeah, so 6 parts will be there, such that support of A is the set of parts of the partition.
Ma'am, 0 won't come. 5, 4, 3, 2, 1, 0.
Right. 0 will be there. Yeah, anyway, we need 6 positions. Yeah, exactly. Thank you. Yes. So lambda we need to find out. Again, that will be 6 places. Okay. So 6 places. Yeah. And is the unique partition lambda such that support of A, and now support of A is this, is the set of parts of the partition this. So what will you do? So it should, these are the parts. So what I mean to say, is this order? Okay, partition. So we'll write it in a order. So it will be kind of weekly decreasing thing. Okay. So anyway, lambda we always add because we want strictly increasing thing. So let's try to do that. So okay, so you start with 8. 8 minus 5, what will it be? 3. 7 minus 4, it will be 3. 6 minus 3, it will be 3. 4 minus 2, it will be 2. 1 minus 1, it will be 0, and this is 0. So what we did, we will do, so in the support you subtract lambda n, because because support is lambda plus delta n, so you need to remove delta n, which is this, and you partition we will always write it in the form of weekly decreasing thing. So we'll start with 8 and we go down this. So 8 minus 5, 3. 7 minus 4, 3. 6 minus 3, 3. 4 minus 2, 2. And 1 minus 1, 0. And 0 minus 0, this. So lambda is this. Is that clear?
Yes, ma'am.
So this is that partition. So you can write this is your shape of it. So that much we are saying. So let's try to do that in this question. So A is given to be what? 5 1 0 0 3 2 0 4 6 0 0 0. We'll do addition also. So you have that. Now you construct the label WI, which is what? Now how many positions? So this is 0. So I'll change the color. So this is 0 1 2 3 4 5 6 7 8 9. I'm just writing 9, but that doesn't make any sense. That is not required, you can say, but you can go up to 9, and you can write it later on also, but that is not required as such. So you have cell, keep some distance, 1 2 3 0 1 2 3 4 5 6 7 8, and I'll write 1 point here. Oh, okay, that should not be. Oh, okay. So now let's see, this is 0. So this is 0 position. This is 1 2 3 4 5 6 7 8 9. Let me change that. Oh, okay, it's fine. I'll change color later. So okay, 1, and now this is 0 0. Now this is at 4. The non-zero position is 4, and then 5, and then 7, and then 8, 9, and everything is 0. So you have now x0, sorry, x5. So the position is ak, so that should be the value which is there. X5, x1, and next x4 is 3, x3, x2, x4, and x6. Okay, so we have this. Right, now let's calculate whatever we need. Firstly, weight of a. So weight of a is the product x a k raised to power k, and k goes from whatever we have. So now let's do that. So non-zero position we need to see. So x5 raised to power 0, x1 raised to power 1, x3 raised to power 4, x2 raised to power 5, x4 raised to power 7, x6 raised to power 8. Okay, is that clear? How are we?
Yes, ma'am.
Yeah. So this is weight of A. Now support of A. Support of A is the position where it is non-zero. So all those k such that AK is non-zero. So k is what? K is the power.
0, 1, 4, 5, 7, 8.
Exactly. Very good. So this is your support. Now, yeah. Now what is shape? Shape of A. Okay, we can. Okay, let's. Okay. So shape of A is what? Uh, we need to find out. So what we will do, whatever we got as support, will what do we have as delta m? N is your 6 again. So this is what, sorry, the tuple you have, 5 4 3 2 1 0. Now you subtract it. So what will you get? 8, 8 minus 5, that is 3. 7 minus 4, 3. Oh, it's kind of same. 5 minus 3 is 2. 4 minus 2 is 2. 1 minus 1 is 0. Oh, this is the same as in the earlier question. Okay, so shape will be this. Now let's calculate the sign. Sign of A. Let's see where it is going. 1 is going to, okay, sorry. So this is sigma 1. So 1 is going to 6, 2 to 4, 3 to 2, 2, sorry, 4 to 3, and 5 goes to 1, and 6 goes to 5. So this 5 represent sigma 6, 1 represents sigma 5, 3 represents sigma 4, this represents sigma 3, this represents sigma 1, sorry, sigma 2, this represents sigma 1. Okay, now let's see what is the cycle we have. 1 goes to 6, 1 goes to 6, and 6 goes to 5, and 5 goes to 1. Oh, sorry, what I am writing. So 1 goes to 6. Now where 6 goes? 6 goes to 5, and now 5 goes to 1. So cycle is closed. So start with 2. 2 goes to 4, 4 goes to 3, and 3 goes to 2. It is closed. So now, if you remember, this can be splitted in 2 cycles, and this is again in 2 cycles. So this is exactly sine of A is minus 1 raised to power 4. That will be 1. Okay, if you write it in the form of transpositions, so you will get that. Okay, so this is the sign. Now let's see, we need, okay, now the extra thing is, now if alpha is this, alpha 2 1 0 0 0 0, so what is this? Alpha is 2 1 1 0 0 0 0. What does this represent? This actually represent x1 raised to power 2, x2 raised to power 1, x3 0, x4 0, x5 0, x6 0. So that means x1 is square, x2 is 1. So what we can do, we are saying you add a plus alpha. What does this say? This says you multiply as in this multiplication and addition in terms of exponents. So when we multiply, exponents got added. So in that sense, this will be what? So for example, weight of a plus alpha. What will it be? So what you are exact or maybe if you want to write in that form, you can do this also. uh, from in the shape you can add this also if you want. Okay, great. Yeah, what I was saying, so weight is what? A is what? A is given, so weight of A is, we have written it down, this. Yeah, so now you multiply on, in this you multiply x1 square x2 raised to power 1. So what will you get? You will get so I'm writing in terms of weight, so I'm already multiplying. So 5 will be as it is, x1, so this will be 1 plus 2, this will be 3, x 3 raised to power 4, x2 raised to power 5 plus 1 is 6, x4 raised to power 7, and x6 raised to power 8. So this will be, weight of a plus alpha will be this. Now let's try to form the abaci corresponding to this. Sorry, I should say abacus. Yeah, sorry. Yeah. We have this. Okay, so what does this say? This says you are shifting excise two space forward. So so for example, two space forward for x1 and one space forward for x2. So the position is getting shifted. So when the abaci you have okay, let me copy this also. Yeah.
Ma'am,
Yes.
ma'am, the weight of A equal to 5100 means x power 5 power 0. Ma'am, right. And alpha equal to 2100 means
Hmm.
x
1. Yeah.
2 power 0.
No, no. So when we write like this, sorry, when we write like this, we say that this is x1 square. So first letter will represent the exponent of the first one. This will be x21. So this is like m. So this is same as mv or maybe type of t. So this is the type. So type is what you take the powers like this. So this is exactly
Yes, ma'am.
you go for everything. This is just
0,
power
0.
0. So I can only write this.
In weight of A, we write na 5 1
Huh,
means
huh.
x 5 power
Yeah,
0
that is different because we are
question.
looking at the abacus, right there, because this is in the
Okay.
form of abacus. Now let's see what does this represent in abacus only. So now what you are doing, you are saying x1, you take x1 two positions forward. So what you are doing, you take it to here. Okay, so this circle is moved to this. Okay, and for x2 you uh, uh, you forward it to the next step because we are saying just one step ahead, x2 raised to power 1. So you add 1 power, so you will reach here. So now this new abaca and the remaining ones will be as it is. So I'm just crossing this one so that we will not. So black color represent the a plus alpha thing. So here the new abaca. Corresponding to that, let's write it down from the abaca only. How, what is weight of a plus alpha? So what it will be? Now x5 raised to power 0, it will be as it is. Now at one position there is nothing because we have shifted already. And now x1, uh, so x1 raised to power 3, because it is now at the position 3. And x3 is with the power 4. X2 is now not here at the 5th position, it is now at the 6th position, so the power will be 6. X4 raised to power 7 and x6 raised to power 8. So you'll get this now, and you can see this is the same thing. The we written it down as in by multiplying, and we written it down using abacus. These are the same things. Is that clear? How are we getting weights
Yes, ma'am.
of addition? Okay. So now if the question asks other things like support, now support will be what? Support, shape and sign. Let's calculate quickly what is support, shape and sign. So support of a plus alpha is what? Just you take the position. So position is what? 0, 3, 4, 6, 7 and 8. So 0, 3, 4, 6, 7, 8. Also you can write it in the form of a1, a2, a3. So let's write it in the form of a is what? You can write in the form of the a1, a2 form. So this form. You can write it in this form also. So let's write a plus alpha to be. Now how will you write? You write the position. So at 0th position it's 5. At first 1 is now 0, 2 is 0, 3 is 1. So I'm writing AK and position number. So 4, at the position 4 we have 3. At position 5 is now 0. At position 6, uh, yeah, at position 6 is now 2. At position 7 is 4. At position 8 is 6, and now 0, 0, 0. So this is your a plus alpha. So if you write it in this form, this is your a plus alpha. Is that clear? How are we getting it?
Yes, ma'am.
Okay. So support of a plus alpha, as I've written, this will be this, and shape of a plus alpha will be what? Now you have the support, and you know that again you subtract it with 5, 4, 3, 2, 1. So you'll get 8 minus 5 is 3, 7 minus 4 3, 6 minus 3 3, 4 minus 2 2. Sorry, 0 is also there. You forget always. So this is 0. Yeah, 3 minus 1 is 2, and this is 0. So now as you can see, the shape is now changed. Earlier it was 0 0 in the end. So earlier it was now we have multiplied something, so it should be bigger. So this is bigger. Now shape is this. Now sign of a plus alpha. So we'll again write. So now 1 goes to 6, 2 goes to 4, and 3 goes to sorry, yeah, it will be if it will collide, then it will get changed. Sign will get changed only if it will collide. So as you can see, because it will, it if it jumps something, then at that position, so like 3 number will be at 4th number then. So for example, this is your sigma 1, this is your sigma 2, this is your sigma 3. So that 3 goes to 2, and you can see there is no overlapping, because at the previous one it is non-zero, like there was nothing. Okay, anyway, so this is 3 and sorry, sigma 1, sigma 2, sigma 3, sigma 4. 4 goes to 3, 5 goes to 1, and 6 goes to 5. So this is your new one. So again let's see, 1 goes to 6, 6 goes to 5, 5 goes to 1, closed. 2 goes to 4, 4 goes to 3, 3 goes to 2. So this is the same kind of. So this is minus 1 raised to power 4. This is again 1. Yeah, so you'll get the same sign because there is no collision. So if these will collide, then the order will get changed. That's why you'll get the negative sign. So, and that's why in the theorem also you'll get these got cancelled. When there is a collision, then these got cancelled. Yeah. Yeah, this was the last question. Is this clear?
Yes, ma'am.
Okay, great. So yeah, this was the last question. You may ask your question now. Okay, I promised to explain that L cube question. So yeah, the question was the linear order Lk is k factorial Lk plus 1, right? So let's try to do that. So what do we do here? As you know, L dash is L square because when you, so what is dash? So you have this picture, you have something, let's say 1 2 or maybe dots. So you have some dots, dots, dots. Now you add something. So you have this. So you added something. So this is your L dash. Okay. So in the linear order, there's a order. Now you added uh, star.
Yes, ma'am.
Now if you remove it, so you'll get this into this. So you'll get this. So this will be L and the other one will be L. So this will be L square. So this is L dash is same as L square. You can give a isomorphism. Now if you do L double dash, what is this? L dash dash, right? So what you are doing now, you have now L dash is L square. So L just construct it like this. So this is your L square. So you have this L square or L dash, whatever you write. So you have something of order, let's say this is your linear order, and you have something, 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 let's say more, and thing. So you have this order. This is your L, this is your L. Now you add some. Now this is, now you are saying, you are talking about L dash. You add some. Now you are saying over L dash, you again do the derivative. So derivative says you add star. Now to add the star, you can do it on the left or on the right. You have both the options. So what I mean, so over these lines, you either add here star. Okay, you can have it here or you can have it here, not simultaneously. So I should write. So you can add a star here. Then when you add a star here, you will again can, so this will be your this, and then you can break it and you will get this. So what I mean, so you'll get, when you break it, so I'm just not drawing. So this is like your L. Now this is your L. Now you break it, you will get something, the other L. So you get L cube. Okay. Now the same thing, this star you can add at this side also, right? They, both options are there because you are, so you can think of in this, so why we say derivative, because this behaves, the type generating functions and all these things behaves as the usual derivative, usual differentiation thing. So what I mean to say, when you can add it on the right, you can add it on the left. So so for example, if you need to do fg dash, first you can do it for f, you can apply the chain rule, and you can do it for g also, right? So exactly what is happening here. So on the right you can add it, or you can add it on the left. So that's why L double dash is your 2L cube. Is that clear how we are getting 2?
Yes, ma'am.
So and now if you want to keep it 2 factorial, now you got three parts, right? You got three parts, 2 is already there. Now you are talking about third one. So you are saying 2 factorial L cube and you do it dash here. So 2 factorial, you can take it common. You want this. Now in this L cube thing, now this is your L cube. In this L cube, this one I am talking about this one. So in this L cube, now star can be added at any of the part, either this or this or this, right?
Yes, ma'am.
So now you'll get three options. So L cube 3 will be what? L cube dash will be 3 into L raised to power 4. You'll get 4 now because 3 is already there. Maybe you do it from this part. So you'll get 4 parts now with 3 multiple because you can do it on any of the side. So you'll get 3 factorial L4 and you go on, so you'll get n factorial L plus 1. So this is your 3 times derivative and you got 4. So that's why k factorial L k plus 1.
Yes, ma'am.
Is that clear now?
Yes, ma'am.
Okay.